Alright, so the topic is vectors in Rn. So as a starting point for this lecture, let's talk about what Rn means. So Rn is some sort of dimension, for example, r to the r1, which we normally don't write this one here, but that is the set of all real numbers, so that would just be your standard number line. R2 would be the coordinate plane where we have x, we have y. R3 would be three-dimensional space, which we live in. That looks something like this, right, and so forth. So the general way of representing Rn is the set of, we have n components where the ith component exists in R. For, I is between 1 and n. So we can write this sort of set as a vector, and the way we write that is using some sort of bracket. So we denote a vector with an arrow on top of it, so we say this vector v, and we put a square bracket and we say it has, some number here, component 1, component 2, component n. And this vector, since it has n components, where we have ci existing in R, so I'll go ahead and make this standard notation, and v would then exist in Rn because it has n components. Okay, so let's get down to some properties of vectors. So vectors, we can actually add them, we can do some scalar multiplication and so forth. So let's take a look at that. Addition and subtraction is very simple for vectors. We simply just remember that we can only add vectors of the same dimension. So, for example, we can add a vector that lives in R2 to a vector that lives in R2 as well, and we just add across. So we get -6 and 7 here. And same for subtraction, it would just be very simple arithmetic. Alright, let's take a look at the geometric representation for addition and subtraction. So let's again use vectors that exist in R2 just to simplify things, and of course geometric representation only makes sense when you're talking about usually only R1, R2, and R3 because we can't picture R4 and higher dimensions. So let's say we have this vector v here, and then we have, say this vector u here. In order to add them, we think head to tail. So we can move this u to here, and this does not change the value of the vector when in standard position because we only care about its length here. And then we just have this, and this vector is v plus u. So I would encourage you to just pick two random vectors, calculate them arithmetically, and then graph them like this, and see if the sum you get arithmetically is the same as geometrically. Let's go ahead and see if we want to subtract things now. So let's say this v again. We have this u again. Say we wanted to find v minus u. So what is that geometrically? We point towards towards v, the positive away from u, and we can see that this makes sense thinking back to what we did with addition. U plus v minus u, head to tail, is equal to v. So again, you can check that arithmetically and then graph it to see if it makes sense. Okay, there are some interesting vector identities that you should be familiar with. They're really easy to show if you were to just write out the vector in components. So I'll just prove the first one, and then you can try to prove the other ones as exercises or just make sure they make sense to you intuitively. So we have maybe, I'll be consistent, and since that vector is called vector u, I'll do u1, u2, un, and of course these again only make sense if they're in the same dimension. We have v1, v2, vn, and that is equal to u1 plus v1, un plus vn. And then on the other side, you know, if we were to just switch them, you can already see what it's going to be. Fortunately, v's and u's look kind of similar, but we can match up their components and see that v1 plus u1 is equal to u1 plus v1. Alright, so you can go through them. Quick thing on notation, again, arrows are vectors, and the letters without arrows are just real numbers. So they're what we called scalars because they just live in Rn. Okay, and just one final vocabulary term. Standard position is what we call a vector where its tail starts at the origin. So we can actually move around this vector v to say here or say here. As long as it has the same length and the same direction, it is actually the same vector, but in order to standardize everything, we always measure how the components of this vector in terms of it in standard position. So for example, its x value is 3 and its y value is 2. So that would be v. Alright, so that's vectors in Rn.